we'll move on to our first presentation today. Brandt Winkleman with Fairweather IT is going to talk to us about aerial bathymetric survey data fusion. Brandt Winkleman is the Technology Solutions Manager for Fairweather IT, an applied science and technology business based in Bozeman, Montana. He has a bachelor's in environmental physical science and a diverse background in electronics, fabrication, integration, and geospatial science. Brandt has worked as a GIS manager and data analyst at the university and ecological nonprofits in both Montana, Wyoming before joining Fairweather IT. So please, with a warm welcome, can we welcome Brandt?
All right, thank you. Thanks for making it out to the early show this morning. And today I want to share a few ways that we've dealt with answering a question I think we probably all ask ourselves from time to time while you're sitting in an office somewhere, and that is, I wonder what's going on down there or over there or somewhere that you can't really access very easily. This thing's not going. The laser pointer was on.
No, that was my fault.
Oh.
There we go.
Perfect. Thank you. So, just a little background. Like was mentioned, we are an applied science and technology service in Bozeman, Montana. We do a variety of things with all number of drones, both surface and aerial. We do some remote sensing work, thermal mapping, photogrammetry work, of course. We do some water sampling from UAVs, and we also have a small fleet of USVs, which is uncrewed surface vehicles instead of aerial vehicles, so things like boats, and a variety of other random special projects. Some of the equipment we use is in the UAV category, this Wingtra 1, which is what I'll be talking more about today. That's the orange VTOL that you see there, that stands for vertical takeoff and landing. It's like a little plane that sits on its tail, takes off like a regular quadcopter drone that everyone's used to seeing, and then turns and flies like a plane. We have also a number of heavy lifting drones that we do some water sampling work with, and there's a picture in the bottom of a few of those big guys. USVs, today I'll talk a little bit about this Zissou bathymetry boat. That's that orange boat up here on the top. If there's any movie buffs in the room, that name is from Wes Anderson movie, Life Aquatic. Bill Murray's character in that, Steve Zissou, so that'll come up again. And we have a number of other boats that we use for waterfowl hazing out at the Berkeley Pit, which you may have seen some information on last year. We've been working on a drone swarm, which is a little fleet of 6 boats that all kind of go out and work together. And we have some ground-based stuff to test things out because, as we know, there's a lot of ice on the water a lot of the year around here, so it's tough to test boats most of the time. We also do use some ROVs, which more acronyms, of course, but that's just remotely operated vehicle. These are things like little submersibles for doing underwater inspections. So that did not seem to advance. Well, the end. Well, that went by fast. No questions, please. All right, so some of the field work we do, where do we work? We typically do most of our work in the mining remediation sites around Butte and Anaconda, on occasion elsewhere in Montana. Today I'm going to talk a little bit more about some of the work we did at Warm Springs Ponds last year. So I'm sure the vast majority of people are familiar with what Warm Springs Ponds is and where it is, but for the sake of completeness here, it's a big pond complex that's just up by the exit for Anaconda, very close to where we're at. You know, we're currently right down in here. This is the whole pond complex. You can see the Berkeley Pit and Yankee Doodle over there, so all kind of right here in the region. Just a little bit of history on Warm Springs. It's about a 2,500 acre complex. It's still being used for water treatment and sedimentation. It's also a fish, wildlife, and parks management area, and offers up a number of recreational opportunities for people and a pretty diverse ecological community of migratory birds and other things. So the survey work we were doing out there is sort of to go back to answer that question. I wonder what's going on down there. It was in the bottom of the water. You know, these water bodies have been in place for a long time. They're used for collecting sediment, so conceivably they're different than however they were when they were built. And so what we did was go out and collect an aerial survey with that orange Winktra to get a surface model of what's above the water, and then this Zisu boat outfitted with some bathymetry equipment to get an idea of what the topography is like below the water. And you can see some pictures there in the bottom that are just kind of representations of collecting data in those two environments and how they're adjacent to each other. So first I'm going to just play a little video that's kind of an overview of the work done out there, and then I'll go into it a little more if you want to start that. Do you have that video up?
It's a good thing you're pretty relaxed.
Yeah. All right, so this is just going to be a little walkthrough kind of the two types of field work going on, just so you can kind of have a little context of what goes on out there. As mentioned, we have this boat that's outfitted with a sonar, and then the plane's got an optical camera in it. We also have GPS base stations set up during this because they're taking in RTK or PPK GPS correction, depending on which craft it is. Here's just a little video of this thing taking off. It's pretty impressive. It handles wind and takes off and lands itself, so you mostly just stand there and cross your fingers. And then this collects a bunch of imagery. This is kind of an overhead view of all that imagery stitched. Then on the water side of things, here's an example of just that boat going around on its survey tracks. I'll talk more about all the stuff on here, but kind of just a close-up shot, and as you can see, it's full of different kinds of equipment for all kinds of communications. Tough day in the shade there under the ground station, and that's kind of a view of what we have the ground station set up, and we built that system as well with some screens so you can see what's going on the boat and control stuff from land. And then, here's just one little sped up thing of it doing its survey line, making a turn, very dramatic turn for cinematic effect. And yeah. So there you can see kind of all the sound returns collected on the water in that larger pond, and then sort of a similar data collection in that middle pond. That's sort of what it looks like coming back from being out in the field. And I believe that's the end of that, right? So now to just talk about those individually a little bit. As I mentioned, we use this Wingtra to go out and do the aerial survey. It's got a 42 megapixel camera, so it's taking really high resolution images. To cover this whole area we were working in was about 13 flights. You fly at about 400 feet off the ground and with 75% overlap. So what that means is, from 400 feet, a picture will capture whatever space that is below it there in its field of view, and you want 75% of that picture in the next line and the next line, and then that's sort of the base of how that photogrammetry can build a 3D surface, because one point will be in, maybe 50 pictures or something, and from all these different angles, and so it can kind of get an idea of how to model the surface just through imagery. We covered about 3,000 acres there and collected over 28,000 images. As you can imagine, 28,000 images from a 42 megapixel camera is a pile of data. And yeah, there in the bottom you can just see the GPS base station area. This plane's set up to use post-processing correction, so it's not correcting back and forth to the plane the whole time, but you can correct the geolocation of all those images back in the lab. And then this is sort of just some shots out of the processing data just to kind of get an idea of like, well, what do you do with all these pictures once you have them? So we use Pix4D. The picture on the top kind of shows you can see sort of a green sphere at the top. Each one of those is a place where the plane took a picture, and then there's kind of a pyramid with a little representation of the picture below it. So, that's sort of a visual of how many times it's taken a picture flying up and down these lines. And you can see them tilted if the wind blew and it is trying to correct itself. So all that information about how the plane was oriented is tied to those pictures too, and then those are all geolocated with the GPS data. So pretty dense and accurate data set. And then there on the bottom, on your left here, we have kind of this is the aerial image, and then this is that sort of 3D surface that it comes up with, and then kind of the combination over here, this isometric view. You can see the 3D relief. There's, a building sticking up and the lime silos sticking up, and you can see the river channel. So it's just kind of a rough view of what does this 3D surface look like with that aerial imagery draped over it after processing. So that data comes in with a pixel size of 1.73 centimeters. So one pixel in that picture is about the size of a quarter. And so that whole site is really high resolution mapped. And each of those pixels is in its geolocation within 2 times that pixel size. So 2 quarters in the X and Y and 3 quarters in the Z. So it's really a pretty tight representation of what's down there. So that is sort of what we come back with, this huge composite. In the sort of zoomed in spot here on the bottom, I overlaid some water boundaries so you can kind of see, like, it tries to collect or stitch pictures over the water, but the water is sort of, there's no features, so it really can't do it, and the data's kind of junk out there. Okay, well, that's where the next piece comes in is taking the boat out. We got a decent look at the above water ground. Now we want to know what's going on underwater. So this Zissou boat is something that we developed and built in-house. It's set up with a single beam, dual frequency echo sounder. So that's a thing that makes a sound. It goes flying down through the water column, bounces back, and gives you an idea. This is, whatever, X depth away from you. The equipment on here was designed for taking out on the Berkeley pit, so that echo sounder is kind of overkill and actually meant to go really deep, but we had it, so this is what we were using this time. We use a program called HiPAC to acquire the data, and this boat has, in this gray box back here, has an onboard computer, just like kind of a shrunk down version of a desktop or your laptop or whatever, and that's running all the software. So it's as if there's someone really sitting there in that box with a computer running all this equipment on there. And then we use radio bridge, which is what some of these antennas up here are, to basically remote in, just like if you were working from home, remote into your computer back at your office. Well, our office is this boat in this case, and we're sitting on shore, remoted into that. And that allows you to control all the equipment on there, but it doesn't require that radio link back to shore to get your data. So it's all just happening on the boat, and it's safe. Even if it runs aground, you could go get it, and you won't have corrupted anything because it's just running right there, and it didn't need to come back to land. So picture on the top is looks like I'm hard at work. It's a hard-earned day, though. There's a lot of months of banging your head against the wall to get things to work before you get to just sit there and enjoy the boat doing your job for you. But so here's sort of another close-up of that ground station, which I'll talk about in a second. So going out there, we bring in 40,000 sounding returns. Again, pretty dense data, certainly nothing like the imagery. We did that over about 8 missions, did 50-meter spacing on those lines, survey lines, and ended up running about 50 miles of survey line to cover all of that, and about 850 acres of surface water. So looking at that ground station, you can kind of see what we're remoted into there. This screen shows the survey job, in that all those yellow lines are just what the boat's doing, driving back and forth, collecting data. This screen is the remote desktop connection to the computer that's on board, and this is a live stream of what that sonar is reading and collecting. So you can control that from shore. And then down here, there's another representation of some data coming in. And we have a point and tilt zoom camera on it, so we kind of have eyes on it if something goes wrong. At times, the boat's a mile away from us, so it's nice to have eyes on the craft as well. And to tie it into the water session, there's also, we didn't have it set up in this picture, but we also run a multi-parameter sonde, if anyone's familiar with one of those. It's a water quality sensor that does, it depends on what you have plugged into it, but we do pH, ORP, dissolved oxygen, conductivity, things like that. So we can also go out and plug that into the computer and stream in surface geochemistry data the whole time and make kind of a surface map of that as well. So after all that survey work, there's Bill Murray's character, Steve Zissou, and giving us the go-ahead on all that data collection. And as you can see, it's quite a network of lines and points out there. So, okay, we got all our data. What are we going to do now? Well, of course, you just have to merge it all together and make sure you select to just do it without any kind of problems, and then everything's fine. That's usually what we forget working on computers, is the do it without any problems thing. So of course that doesn't work. Some things to consider though, trying to smash these two data sets together. You know, every software package has different file formats, so you got to deal with that, of course. We're trying to take a bunch of point returns and a bunch of pixels and make them mean something together. Some of that data is in elevation, some of it's in depths. There's differences in resolutions between the data. And, you know, I showed that the water boundary and how the aerial data is useless over the water. So, well, how are we going to clip out what's good and what's bad? So going through some of that, you know, first thing is we need something from points to pixels because we already have a bunch of images and we're not going to try to change all that into something else because it's a massive data set. So trying to interpolate a surface out of that, you know, you can see out here sort of in the middle, like, sure, that looks reasonable, but something tells me this is totally useless. And likewise all the way around it. So you can't just, you know, make a surface and then everything's okay. So, all right, well, what do we need to take into consideration to get this usable to represent the whole body of water? Problems with that picture on the left, you know, we're not generating any useful data beyond wherever there's a point. Lo and behold, you don't have any data feeding into it. Of course, it's just made up outside of there. The surface that we have there is never going to capture the edge of the water because we didn't drive the boat on the ground all the way around the edge of the pond. You know, without that shoreline representation in there, you can't really truncate that body of water in the data set. And you know, it's best practice also not to have the turns for the survey lines in there. So we need to cut those out. And you know, looking at this, if you wanted to know out in the middle here, yeah, that looks reasonable. And if you just wanted this piece right here, that's great. You clip back into where you've actually got data. But if we want to go, you know, out to the edge of the water, ideally, we would even want to interpolate beyond that so we can clip back into good data and have a reasonable story. So how are we going to accomplish that? Well, obviously we have to add more data to it because the boat just got what it got out on the water and it didn't go to the edge, and that's the piece that's lacking. So we have the good fortune in this situation to have a very high resolution ortho image of the whole place, so you can digitize out a water boundary that's super accurate and call that your zero depth, which we have the GPS elevation from GPSing that water level on that day, so we have a pretty good idea where that's at. And then to get them into points, just kind of do a subsample along that line of points at a given distance, and then we can kind of fortify that bathymetry data set with all that shore data. And to try to improve to be able to go beyond that water boundary that we want to clip back to, well, we so happen to have a really high resolution surface model of the bare earth. So again, I made just a buffer around that and kind of an even sampling of elevation points that we have from that Winktra. So now we have a situation where we've got all the bathymetry pings from the boat, and we've got some data around the shore that represents the actual real edge of the water. And then we've got some more data beyond the shore so we can interpolate out past what we really want. And so we have all this real data that we can kind of enrich that data set with, and then get everything on the same page with elevations, because the bathymetry is at depth, but we know the water level's at whatever elevation, and then just do math to get what was the elevation at 5 feet deep or 20 feet deep or whatever. So what that looks like is then we have, this is just a visual of that. We've got our survey lines, all these yellow dots that are just representing whatever the water elevation was, and then, all these that are representing, in this case, the dike along there. And we run that back through that interpolation and clip it back to that water boundary. Now we have something that looks, hey, that looks like a water body. We're definitely on track here. So another sort of visual way just to look at this is, this one on top was that first one that's got all kinds of made up nonsense outside of the boundary, and that black line is just the water boundary, the shape of the lake. Again, it looks reasonable down inside the water area where it's blue here, but none of this was good for anything. And if you tilt it down and lay it out, you can see none of that ever even got up to that water boundary because we didn't ever tell it where 0 is. So after doing all that work here, we end up with something that is clipped to that water boundary and a realistic looking version of what those dike structures look like around that water. And it's really coarse data because the bathymetry data is not a 42 megapixel camera pretty much. So it's a little more blocky than the imagery. So now what? Again, now we go back to merge and pick without any problems. And I'm sure there were still problems, but we're at a place now where we have, here's our aerial image, and you can see there's water or data out over all that water, but we don't want to use that. But we have our nice clean bathymetry data that goes all the way to the edge of the water in both of these ponds, and we can just merge those together and say, well, anywhere where they overlap, make sure to pick the water. We don't care what the aerial says. And then this is sort of just a mask to cut out, these smaller bodies of water up here. The imagery covers them, so it makes up stuff across there, but it's over water, so it's still useless. So we want to clip out all those little other water bodies, and these are all digitized off of that high resolution imagery. So then our combined thing, we end up having seamless data going everywhere over land, down through the lakes as if they were empty, and back across. One issue here is the difference in resolution. So if I have any geospatial people in here, we all know that the best practice is to upsample to your worst data when you're mixing them together. But in this case, that bathymetry data is really coarse, and it would be a shame to give up all the really high resolution, accurate imagery of the ground by sort of making that so much more coarse. So we kind of did the opposite of what the best practice is there, which is each one of these big squares of water data just gets divided into a ton of little squares with all the same value. In an instance where this data is just going to, the client, and they know the considerations, and that pond is, very flat anyway in the bottom, so you're not exactly overreaching, suggesting that it's the same depth at all these areas in that sort of subsampled block. Kind of allows for that to be less ridiculous. You wouldn't want to do that if you were making this to give to the USGS, and who knows who's going to get it to do what. But this is not that. So anyway, that is the combination of what all that stuff looks like, and how we get there. So some of the issues we encountered are, one, as I mentioned, that Zisu was designed to be out on the Berkeley Pit, so it's a big boat. It sets a little lower in the water than you'd want for something like this in these shallower ponds, and the echo sounder is just totally overkill because it's good to, thousands of feet instead of 20 feet. And there's a lot of seaweed out there. As you get out later in the year, you can see here's a raft of it that we managed to get stuck in right by shore when it was turning around. Luckily there, we could just stand there and figure out how to get it off. But, if you get that happening half a mile away from you, it's pretty hard to see what the right move is. And so you can see actually in this all this black area in this pond we weren't able to get out into because by the time we got out to do that survey, it was so weedy. There's seaweed all the way up to the surface of the water, and you're not going to get around in that. So some solutions to that are, one, go out earlier before there's the weeds in the pond, and two would be a smaller boat. Now, to continue the Steve Zissou joke, we have built another boat this winter, and Steve Zissou's sidekick was Klaus, so we named the boat Klaus. And this is just a boat that sets much higher in the water, and it's outfitted with a more appropriate echo sounder for shallow water work. And then we're actually going to take that out probably next week and see if we can get into some of that other water we were skunked on last middle of summer when we got out there. So I'd like to thank our collaborators on this, and if you want to see any other fun videos of drone stuff out in the field, you can check out that YouTube channel of ours, and otherwise I'm happy to take any questions anyone might have.
Thanks, Brandt. Any questions?
So for the Zissou,
Yeah.
what was the minimum depth you could accurately capture data?
I think it sort of falls apart at about 1 meter, which is why we kind of stayed away from the shore too. It's the new one we have. That sonar is a higher frequency, and it can go, much shallower. So, yeah. But the way those bodies of water are shaped, they get really shallow in the last 10 feet going along the dikes or whatever, and then before that they're kind of all the same. So we were able to sort of stay out in the deep and then forfeit the shallow and kind of use that shore method to kind of fill in between.
And what was the max depth that you found in Pond 3?
It wasn't that deep. Like, I want to say it was like 20-something feet.
Thank you.
Yeah.
Go ahead.
Are you able to increase the density of your bathymetric sampling, like if someone wanted tighter data cells? And then my second question is, how functional is it in super contaminated or cloudy water, like some of the reservoirs in eastern Montana?
Yeah. I mean, we can set up a survey to be as tight as you want. Really, a couple considerations. There's one, if it's really deep, that angle, focal angle, or whatever on it, you're covering a huge area if you get down pretty deep. So there's not a lot of point in having a close, second survey line, because, like, say on the Berkeley pit where it's really deep, I mean, I don't know exactly how big, but that's probably well beyond that 50-meter spacing that we might have done. So you're kind of collecting the same piece of information twice, and that's going to return off sort of whatever the first thing it hits is. And there's ways to kind of see how that's working in the echograms on those, but. So you can do it super dense in something shallow. That'd be totally the way to do it. So we might be able to do more dense, especially with our newer, smaller echo sounder. And then, sorry, what was the second?
Cloudy water.
Oh, cloudy water. Yeah, cloudy water is a problem. I mean, you could see the seaweed in where we did go over it. There's just kind of this layer of all kinds of noisy reflection, and then actually, my colleague went to a training thing with the high pack people, and he brought that data, and they were like, "This is the messiest stuff we've ever seen because of the seaweed is giving you all kinds of returns that you're not interested in." So that is why we want to get back out there now, and just the way things worked out last year, we got pushed off until way too late in the summer when that had warmed up and started growing.
So I don't recall if you spoke to this, but on the Winsta data for the aerial survey, how would you correct the Z for heavy vegetative or tree canopy? I know you didn't necessarily have that there, but how would you do that? Would it have to be ground truthing?
Yeah, well, so I don't know exactly how it works, but that Winktra data or the Pix4D software does have some kind of algorithms they use for doing a terrain model and a surface model, and one of them is like removes your truck that's sitting there and buildings and big trees and so is it going to remove grass? I don't know, probably not, but yeah, anyway, there's some processing steps in that software to clean it up to a point. Yeah.
Got one more over here.
Okay.
So I have one comment and then two questions.
Okay.
The comment is, the Zizou's a real upgrade, but I do miss the Ghost pirate ship that was out here a few years ago.
Yeah. Yeah.
The Wingtra, how, as a practical matter on ground, how far out can you fly that before you lose visual line of sight?
I don't know. I mean, we were able to see it in all of our surveys, and we were probably flying, maybe not all the way across like Pond 3, but that's like a mile. It's pretty bright. I mean, it depends on the day too, but it does show up actually quite well compared to, a lot of our other drones and stuff, or black carbon fiber things, and they do tend to disappear before they probably you'd think they would. But that orange one does show up for line of sight quite a ways.
Okay. And then do you have any plans for developing a submersible?
Well, yeah. So one of those slides we have two different submersibles with like 1,000-meter or 1,000-foot tether, which is basically just an Ethernet cable that's connected to it. So you have it hooked up to a computer, and then you can go down and inspect a dam or whatever you want underwater. Go down and grab something with a grabber, or take pictures, or any of that kind of stuff. So we do have a few things for that, but they are tethered, and we don't have any kind of RC versions of that. It's tough because the water kind of makes the radio control not work. There are ways that people are starting to do that by having equipment floating around out on the water that they can use for communication instead of trying to go radio back to land. But yeah. Does that kind of answer your questions? Great.
All right, thanks, Brandt.
Yeah, thank you.